Good morning, everybody. Our topic today, we're continuing the discussion of continuity, which we started last time. Let me remind you that f is continuous at the point A if the limit of f as x approaches A exists and happens to equal the value of f at that point. In particular, f, of course, has to be defined at that point. It's a pointwise definition. It's a pointwise definition. And we generalized it to intervals by saying f is continuous on an interval if it's continuous at any point in the interval. When it was an open interval, it was a very easy statement. For closed intervals, we had this little minor modification of what it means to be continuous from the right, what it means to be continuous from the left. And for a closed interval, you want the function to be continuous from the right at the left endpoint and continuous from the left at the right endpoint. Remember? Everybody? Okay. So what I want to discuss now is discontinuities. Discontinuities. I hope I spelled that right. And I want to do it using a sketch. So here's our xy coordinate system. Functions are blue. You all know that. So suppose this is the point A, and I want to explore what various sorts of discontinuities can happen. They're different in essence. So the first sort of discontinuity is the following. Suppose this limit exists, but unfortunately, it's not equal to the value of f at the point A. So a picture of that would be maybe something like this. Here's f. At A, I'm going to exaggerate here just so you can clearly see it. At A, so the limit exists, right? The limit exists. As x approaches A, there's an L, but the value of f at this point happens to be here. Okay? So this function is not continuous, right? And this sort of discontinuity, where the value at the point happens to be different than the limit, is the kind of continuity that's the easiest to fix, right? Have you ever played with marbles when you were children? You do this, and you send it right back to where it belongs, right? So this is called, a discontinuity like this is called a removable discontinuity. That's the terminology that we're going to use. Okay? So the definition of a removable discontinuity is the limit exists, but is not equal to the value at the point. Okay? In particular, we will say that there is a removable discontinuity. Maybe we'll write that. So I'll bounce back and forth between these two boards. So removable discontinuity, limit f of x approaches A, exists, but not equal f at A. In particular, for a removable discontinuity, we're going to allow f not to be defined at A at all. We're still going to call that a removable discontinuity. Classic example, sine x over x. Remember this function? We drew it on the board We discussed it. And the value of the limit as x approaches 0 is 1. That's a famous limit. Right? It looks something like this, if you recall. Remember? So the value of the limit as x approaches 0 is 1. However, the function is not defined at 1. So, let alone, the limit doesn't equal the value of the function. Sorry, the function is not defined at 0. So in particular, the limit does not equal the value of the function at 0. So 0 is a removable discontinuity. So x equals 0 is a removable discontinuity. How do you remove it? How do you remove this discontinuity? Right, right. Define f of x equals sine x over x if x is not 0, and 1 if x is 0. So if we define this function, then f is continuous at x equals 0. Does everybody agree? Good? Clear? And if we define it like this, but put here any value other than 1, then we didn't fix anything. It's still not going to be continuous. Clear? So this is the notion of a removable discontinuity. Everybody good? Okay. Back to this board. Back to this board. Let's call this point here now A. A new fresh name for it. Same name. Never mind. We can handle that. I want to use A because I want to stick to this. So here the discontinuity is going to be something harder to fix. So the discontinuity is going to be what's called a jump discontinuity, and it's this case here. Suppose f looks something like this. Okay? And it doesn't really matter what the values are at the point, because by playing with the value at the point, you're not going to be able to make this continuous. Okay? So let's just, for the sake of the drawing, assume that the value is here and an empty circle here. So this is called, so this is a removable discontinuity. Or the arrow's not pointing in the right place. This is a removable discontinuity. And this is called a jump discontinuity. And it's more essential. It's more, what went wrong? Not the fact that the limit doesn't equal the value at the point, but the limit itself doesn't exist. The two one-sided limits are not equal. Clear? And do you see why it's called a jump discontinuity? See, I jumped now. Just to... Okay, so let's write that. Jump discontinuity. So this is the second kind of discontinuity. Both one-sided limits exist, but are not equal. Hence, the limit doesn't exist, and in particular, it can't be continuous. Okay? Example, take any form of step function. For example, suppose it's 0 on the negative numbers and 1 on the positive numbers. So this one has a jump discontinuity at 0. F of x equals 0 when x is negative and 1 when x is, let's say, greater than or equal to 0. it has a jump discontinuity at x equals 0. Okay, x equals 0 is a jump. Sometimes we will just say jump rather than jump discontinuity, because it's clear what we mean. Good? Okay, so back to that board. There's a third kind. So let's be original and denote this point by A.
This one you didn't fix it, right?
Hmm?
You didn't fix that.
Well, you can't, good question, you can't fix a jump discontinuity without tampering with the definition of the function on a neighborhood. So changing the value at the point cannot fix this. You're going to have to either, imagine taking the whole thing and, okay, that's a major change. You're changing the function on infinitely many points, right, on a neighborhood in order to fix it. Okay, and usually we won't be fixing jump discontinuities. Clear? Okay, so the third, back here, the third type of discontinuity that we're going to have is a discontinuity where things go very, very wrong. Namely, at least one of the one-sided limits doesn't exist at all. Okay? So, for example, you could have something like this. So, this is often called an infinite discontinuity. You would also find the terminology oscillating discontinuity. Oscillating stemming from the situation where you have something like sine of 1 over x. Remember sine of 1 over x, that accordion phenomenon, where there's no limit because it oscillates like crazy? Remember that? So that's the situation where the limit doesn't exist at all, at least from one of the sides. So let me write that. So the third type is infinite or oscillating discontinuity. And that's the situation where at least one of the one-sided limits, at least one of the one-sided limits doesn't exist at all. So when I say doesn't exist, I mean in the finite sense. So if the limit is infinity, we said this several times throughout this course, when we say a limit exists, we mean it's finite. Okay? And when it's infinite, then, okay, so I'll emphasize that, doesn't exist or not finite. Okay, and an example, sine of 1 over x, which again we drew several times. I'll make a really rough sketch now because it takes time to draw it accurately. Remember, it was this thing. Remember? Something like this. So this one has a x equals 0 is an oscillating discontinuity. I think the term essential is also used, yes. Okay, the terminology is not necessarily consistent. Okay, so yes, I think it's also called essential. That's the terminology used in Hebrew, by the way, the translation of the word essential. Okay. So those are the kinds of discontinuity that we will encounter. I want to quote a theorem. I'm not going to prove it. It's not a very easy theorem to prove. It's not, just working closely with the definitions. There's a bit more to it. But I want to quote it. And the statement is, if f is monotone on some interval, then f has only jump, or not necessarily has, f might have, it could be continuous, of course, but if it's not, it might have only jump discontinuities. Okay? And the statement why that is true, so I'm going to wave my hands a bit. If you think of a monotone function, let's say it's monotone what? Increasing for you, yeah. Monotone increasing function, okay? Do you agree, first of all, that it cannot have removable discontinuities? Because for it to have a removable discontinuity, it would have, oops. I have to say oops again because you missed that because this dropped. Oops. So if it's monotone, if it were to have a jump discontinuity, then the limit would have to exist, but the value at the point would have to be here. Right? That's a removable discontinuity. This is not a monotone function. Right? It goes up and then goes down again to continue. Do you see that? So do you agree intuitively, I'm not proving it formally, but do you agree intuitively that a continuous function, a monotone function cannot have a jump, removable discontinuity? Do you agree to that? It could have jumps. There's nothing wrong with this. This is still a monotone function. It has a jump discontinuity. Do you agree? Why can't it have an oscillating sort of discontinuity, or an infinite sort of discontinuity, or an essential sort of discontinuity? Intuitively, that's not hard to see either. And the statement that's hidden behind it is that a monotone function always has one-sided limits at any point. Okay? And that requires proof. Okay? But you can imagine that if it were to have, let's say, an infinite discontinuity of this form, then where would it continue in order to be monotone, right? If it goes up and up and up and up and up, it can't continue and still be monotone. Do you agree? Okay? And if it oscillates, well, oscillating is very not monotone, no matter how you look at it, right? So it's intuitively, this is a very reasonable theorem. Do you agree? Okay? And it's useful. It's good to remember. Okay. So, yeah. Okay. So what I want to do now is restrict our entire discussion to very specific functions. Maybe I'll, yeah, I think we can erase this. So, from now until the end of today, both hours of today, we're only going to be discussing continuous functions on closed intervals. So everything we're going to say is going to start with the words, let f be a function on a closed interval from a, b to r, a real function, and we're assuming that it's continuous. All the theorems are going to start like this. And the reason for this discussion is that there's an abundance of theorem for this case. There are specific theorems that are very, very nice. They're very simple to state, and they give you very strong tools to work with, but they only work in this case. Okay? So let's just start. So the first theorem, suppose f is a continuous function on a closed interval. If f at the point A and f at the point B, the values at the endpoints, have opposite, did I spell this correctly? Yeah. Opposite signs, meaning either this is negative and this is positive or vice versa, then you tell me, what do I want to write here? I have a value A. I already heard two people say the right answer. Good. Here's A, here's B. I know that the value of f at A, let's say, is negative, and that B, let's say, it's positive, right? And it's continuous. What does it mean to be continuous? It means that I can draw it without lifting the pen or the marker off the board, right? Intuitively. What does it say about f? Not necessarily monotone. That's not true. It can go up and down and still be continuous. Right. It's going to have a root. There's going to be a point somewhere in this interval where it crosses the axis, where f of that point is 0. Do you agree? Right? Intuitively, why? Because I start here, I have to get here, and I cannot avoid crossing the axis. Oh, yes, I can. I can do this. There we go. So the theorem is wrong. Nah. Okay. So, yeah, this is not cheat or, okay, sorry. I can try not to cross, but eventually, if I'm going to get from here to here without lifting the marker off the board, there it is. I had to cross at some point. Do you agree? So there's going to be at least one. It may be that I'm crossing several times. Okay? So then there exists a C in the interval such that f of c is 0. Does everybody agree intuitively to this statement? Okay? We don't prove many theorems in this course. We prove some as examples. We prove some where the proof is illuminating. And this one is even more special than that. The proof is a very useful algorithm, okay, for finding roots of functions. So I'm going to prove it. It's called the Bisection Method. So let's prove this theorem. So here's the interval AB, slightly bigger than before, so we can see what's going on. And we're assuming, so I'm going to sketch the idea. I'm not going to write everything. You'll see why in a second. It's going to be very tedious to write everything I'm going to say now, just the idea, but it's very formal. I'm not relaxing the formalism in any sense. So assume, without loss of generality, remember that sort of expression, without loss of generality, assume that it's negative at A and positive at B. Can I assume that? Okay. I'm going to find that point where it must intersect the x-axis. So first of all, I'm going to look at the point E. Let's call it H. H. H for half. H is exactly the midpoint of the interval. Exactly at the center. Half. H for half. Okay? If I was lucky, and the value of f at h was 0, then I'm done. Do you agree? If I wasn't lucky, and chances are that I'm not, then what are the two options? Right. Either it's positive at h or it's negative at h. Choose. I didn't say you, I said her. Negative. Good choice. Negative. So I look at the midpoint. It's going to be either positive or negative. Let's say it's negative. Okay? Now I know that somewhere between here and here, because here it's negative and here it's positive, my intuition tells me here it's going to have to cross the axis. Do you agree? So I'm going to denote this A, I'm going to call it A1, and this B, the original B, I'm going to call it B1, and this H I'm going to call H1, and now I'm going to rename everybody. H1, I'm going to also call it A2. And B1, I'm going to also call him B2. And then there's a midpoint here, which I'm going to call H2. If the function happens to be 0 at H2, good, I'm done. If it's not, then the value at H2 is either positive or negative. Positive. Fine. Suppose it's positive. Now I'm going to look at this interval. I'm going to call this point here, I'm going to call it also A3. And H2 I'm now also going to call B3. And I'm going to look at the interval A3, B3. It's negative here, it's positive here. Let's look at the middle, H3. If it happens to be 0, I'm done. If not, it's either positive or negative. Negative. There we go. Now I'm going to call H3, I'm going to call her also A4. And B3, I'm going to call him B4. And I'm going to look at the midpoint, H4. 0, I'm done. Otherwise, either positive or negative. And accordingly, I choose how to proceed in each step. Okay? I'm not going to write everything I said now. Is it clear what I did? Okay? Do you see that this is an algorithm? Okay? You can code it, right? Start with the entire interval. Call A1 the left side, B1 the right side. Look at H1, which is the midpoint. If it's 0, you're stop, exit, done, happy. If it's positive, then take this side. If it's negative, take this side, and then loop. Right? Do you agree? Okay. So what happens eventually? What happens eventually? So everything I said now I'm not going to write, because it's very tedious and the idea is clear. Okay? Just the picture. If you want to write it for yourself, you can do it. Exactly what we said. Exactly what we said with the... Exactly. Exactly like a computer algorithm. And at the end, write the word etc. That's it. Exactly. Either, at some step, the value of the function at En, let's say, equals 0, in which case we're done. We found a root. En is going to be that C that we were seeking, right? Or if that didn't happen, it can never happen. There is a possibility that you do it again and again and again and again and again, and it's never in that midpoint. Okay? But in that case, or we obtain two sequences. A sequence AN, which is the left side of those intervals we were looking at. AN, so this is one sequence, and BN, which is another sequence. So we obtain two sequences, the A's and the B's, satisfying so the first thing they satisfy is that AN is increasing. Not strictly increasing, but increasing. The ANs always go to the right. Do you agree? And BN is decreasing. So does everybody agree to this? Say yes? Okay. So this is one thing they satisfy. The second thing they satisfy is that BN minus AN tends to 0 as n goes to infinity. So Bn minus An is the length of the nth interval. The first interval, the second interval, the third interval, the fourth interval, the fifth interval. The length of each interval is exactly 1/2 of the previous one, right? So as n goes to infinity, the length of the interval goes to 0. Do you agree to that? And they satisfy one more thing. The value of f at all these A points is always negative, and the value of f at all these B points is always positive. That's how I constructed the sequences, right? So do you agree to these three features of these two sequences that the algorithm built? Yep. Okay. So what? So what? So AN is an increasing sequence. AN is an increasing sequence, and it's bounded. Why is it bounded? They all live between A and B, right? So it's bounded and increasing. What do we know about a bounded monotone sequence? It converges. So it has a limit. What is its limit? We even know what it is. Not just any upper bound. It's supremum. Do you agree? Yes. These ANs, A1, A2, A3, A4, they converge to their supremum. Do you agree? Their supremum is something, well, it's going to be bigger than all the ANs, right? But it's going to be always smaller than all the BNs, right? Because all the ANs are smaller than all the BNs. Do you agree? So AN is kind of a converging sequence that converges to supremum, which is somewhere locked in all these intervals, in their intersection. Do you agree? Likewise, the BNs, they form a monotone decreasing bounded sequence. They converge to what? To their infimum, which is also locked in all these, in the intersection of all these AN, BN intervals. Okay? And it takes a bit more formalism to prove, but I think you can agree that their limit is actually the same. Okay? So the claim is there exists a C which is greater than or equal to all the ANs and less than or equal to all the bn's, okay, there exists a C satisfying this for every n. Okay, and we know that this C is none other than the supremum, which coincides with the limit of the sequence an, and the infimum, which is the limit of the sequence bn. Do you agree to this? Are we done? No, why not? Right, we have to prove that the value of f at this C is 0. Then we're done. Okay, all we found so far is that in this construction here, we're somehow zooming in on a point which is in the intersection of all these intervals. But why is f 0 at that point? Okay, maybe this phenomenon continues forever and we never hit that 0. Why is f at the limit point 0? So C satisfies, so claim f at this point C is 0. Then we'll be done. Okay, and why is that true? The values of f at the point, at any point in the sequence an are what? Are all negative. That's how we constructed the left ends of the intervals. They were always taken to be such that the value of f is negative. Remember? And since an converges to C, what do we know about f of an? Why? Why is this true? I agree. Why is it true? Stronger. It's not just Heine's theorem. The statement is this. an goes to C, therefore f of an goes to f of C. What is this? This is precisely the definition of continuity. It was the second equivalent definition last time. Remember? Okay. The second equivalent definition last time, somebody here said no. Ooh, bad boy. Didn't go over your notes before the lecture. Very important to do that every time. The second equivalent definition of continuity, see it in your notebook? Say yes so everybody believes me. Is whenever we have a sequence going to a limit, f on the sequence goes to f on the limit. Okay? So this is by continuity. Continuity of f. So these are all negative. What can we say about the limit? The limit of negative values, what can we say about it? It's non-positive. It could be 0, but it's non-positive. So bicontinuity refers to the convergence. Do you agree that the limit is non-positive? Yes?
Can you explain that part again, please?
Why the limit is non-positive?
Yes.
Because it's a limit of negative values.
But we say it's bigger than 0.
No, this is less than 0. Limit of negative values has to be non-positive. Okay? Likewise, the bn's converge to that same C. So by continuity, f of bn converges to f of C. But the bn's were such that f of bn was always positive. Therefore, the limit is non-negative. Do you agree? So C is a number such that f of C is both non-negative and non-positive. What does that imply? F at C has to be 0, and we're done. Okay? So, one second before the questions. What we proved here, I want to show you that it's an algorithm. And that's how, well, I'm not saying specifically this algorithm. There are other algorithms. This is called the bisection method because we bisect the interval again and again. And that's how a computer works. You ask a computer, you give it a function, and you say, hey, find me the root. If there's no explicit formula for finding a root, like for a polynomial of degree 2, right, the quadratic formula, if there's no such formula, then it has to do some numerical algorithm, and that's what it does, something like this. So it looks at the interval and says, okay, this is the case, let's look at the midpoint. Is it 0? No. Let's look at this interval. Let's look at the midpoint. Is it 0? No. Now look at this interval. Look at the midpoint. Is it 0? No. Now, the computer can't do infinitely many iterations, right? It can only do finitely many. Suppose it does 1,000,000 iterations. Okay? 1,000,000. Just 1,000,000. That's not a lot for a computer, right? A few seconds and it's done. What did it do? It bisected the interval each time in half 1,000,000 times. So it ended up with still an interval, but that interval is tiny. If the length of the original one was 1, then the length of the 1,000,000th interval is 1 over 2 to the power 1,000,000. Do you agree? That's very small. And it can tell you that there is a root somewhere there. Okay? And for any practical purpose, that's enough. It means you know the value of that root up to the, I don't know, 700,000 digits after the decimal point. Okay, it's between 1.576342 and the same 700,000 digits, and the 700,001th digit is 2. That's good enough for most practical purposes. Okay? So that's an algorithm that is really hidden in the proof of this statement. Questions? Yes?
I'm having troubles with number 3 there. Like,
why is this true?
how can I claim that an is going to be negative?
No, not an is negative. The value, that's how I constructed the ans. I started assuming without loss of generality, meaning that you can do the opposite argument.
Okay.
I assumed that this is the case. Then I looked at the middle. If it's negative, I declare this to be A2. And look at this interval.
What happened on the case that A...
If it's positive, I declare this to be B2, and look at this interval.
Okay.
So I name them, I name the points, that's how I did it, by taking the A point to be the left side of the interval, the one satisfying its negative, and I didn't choose. She's the one who told me what to choose. He tried to intervene, but we didn't let him.
What happened on the case that it's going to be go up and down and
I don't care. I don't know what happens between here and here.
Yeah,
It may be that the function between here and here looked like this.
So then the function is not negative. The function of an is not going to be
It
negative.
is. On all these A points, it is. This is A1, this is A2.
Right.
I'm not saying anything on the points in between. I may have missed many, many roots. I don't care. I'm going to find one of them. Okay, there's no statement that the root is unique, and there's no statement on which one this algorithm is going to hit. As far as the proof is concerned, I don't care. I just want to show existence, and I did.
But you can say that
The
the number of roots is odd.
number of roots is odd? No. Of course not. I mean, if you look at a function, a general function,
No, I mean in this case.
what do you mean in this case?
In the closed interval AB, one negative and one positive value, the number of roots will always be
Okay, yeah, that I agree. Right, because if it, that I agree. But this is not a general, okay, yeah, that I agree. Okay. More questions? Everybody good? Okay, so let me show you some applications of this theorem. So back to the theorem. This theorem, which is very intuitive, and I think the proof, you may need to think about it a bit more, about the proof, but I think the proof is very straightforward. It's not, well, I hid the point where we used something tricky, which is the statement that the existence of that C, which is the limit of both sequences, that's not a trivial statement. It's called Cantor's lemma. But I think it's for us, it suffices to believe it in the depth of things that we discussed. But once you have this theorem, how do you practically put it to use? Okay, when can you use this theorem like this? So let me show you several examples. So just a couple of minutes and then we'll have our break. So, example. P of x, I'm calling it P because it's a polynomial, x to the power 5 minus 4x plus 1 has a root in the closed interval 0, 1. Why? Well, first of all, finding roots of polynomials of degree 5 is something we don't know how to do. We know how to do it when the degree is 2, right? Say yes. For degrees higher than 2, well, there in fact exists a sort of, it's not a quadratic formula, but it's a formula using radicals, using roots of various degrees. There exist formulas for polynomials of degree 3 and polynomials of degree 4. They're ugly. The one for degree 4 spans over 2 pages. Okay? Ugly. One can prove that there is no radical formula for finding roots for polynomials of degree 5 and higher. There is no closed formula where you can just plug in the coefficients and there pop up the roots. There is no such formula. And proving that it doesn't exist is heavy mathematics. Okay? It was proved in the early 19th century separately by Galois and Abel. And these people invented a lot of mathematics in order to prove it. They invented group theory, which is a vast field of mathematics today. And that's what is used, group theory and field theory, to prove that polynomials of degree 5, there exists no formula. No alien can come from some faraway planet and give you the formula. It doesn't exist. Okay? Do you know the story of Galois? So Galois was a very bright guy. He proved this thing. And it was, early 19th century. He lived in France, Galois. And apart from being a very bright young mathematician, he was also a revolutionist. Revolutionary. I don't know how to say the word. Revolutionary. And he had buddy revolutionaries, and he was doing all these, I don't know what. And legend has it that at some point somebody insulted his girlfriend, or the story is not very, very clear. But at those times, if something like that happened, you didn't have much of a choice. You asked the offender to a duel, right? So did Galois. But the dude was a mathematician. And he probably knew he wasn't that strong at dueling. I think they used guns and not swords. And on top of that, since he knew he was probably not going to make it, he sat down all night writing letters to all his buddy mathematicians and all his buddy revolutionaries. And the next morning he died. That's a sad story. He was 20. He was 20 years old. And he already proved and invented half of group theory just to prove this. Well, not just to prove this. He did a lot of mathematics. He was 20. I'm guessing younger than many of you. So that's the story of Galois, and thanks to the Galois, we know that we don't have a formula, so what can we do? Well, statement, it has a root. How can we prove it? Well, let's use that theorem. It's a polynomial. P is continuous, since it's a polynomial. So it's continuous on all of R, and in particular, it's continuous on 0, 1. Why can I say that? Why does being a polynomial make it automatically continuous? What's the theorem that I'm implicitly referring to? Right. Elementary functions are always continuous. We discussed that. So it's continuous. What's the value of p at 0? P at 0 is 0 minus 4 times 0. It's 1. Do you agree? 1 has this amazing property that it's greater than 0. What's the value of p at the other end of the interval? At 1, well, 1 minus 4 plus 1 minus 2. We don't really care about what the value is. It's negative. Right? So these three conditions, by the previous theorem, we're done. There exists a C in 0, 1 such that P of C is 0. By the previous theorem. Good?
But if you get in both of them the same sign?
If you take a function and you find that at 2 points both values are either both negative or both positive, can't use this theorem. Not saying there's nothing you can do to proceed, but you can't use this theorem. Good? Okay, one more example. So let's call this example 1. Example 2. Suppose you want to show that the equation, these are very, very standard questions. They pop up all the time in reality and on quizzes and exams. The equation sine x equals x minus 1 has a solution. So at first glance, this has a bit less to do with finding roots of functions, right? But the standard statement is the following. Okay, define f of x to be sine x minus x minus 1. The difference between the functions. Okay? And if I can somehow find an interval where at one point, one end of the interval this is negative, and at the other end of the interval this is positive, then somewhere in between this is going to be 0, and saying that this is 0 is exactly saying this. Do you see that? Everybody? So, yes, if somehow I can come up with an interval such that at one end of the interval this function is negative, and at the other end of the interval this function is positive, then by the previous theorem, there's some point where this function is 0. And saying that this equals 0 is precisely saying that this equals this. Do you agree? Okay? And in this case, you resort to your intuition. You resort to pictures, which you could have done originally. Okay? So let's make a quick drawing. Blue, 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 blue. So here's a quick drawing. What does x minus 1 look like? X minus 1 is this line here. Do you agree? Slope 1 and crosses at negative 1. Sine x is this. Do you agree? Very rough sketch. But for our purposes, it's sufficient. And here's that point that we're looking for. The point where they're equal. Okay? So, usually pictures are not valid as proofs. But the way to formalize this picture is by saying, okay, do you see that at 0, sine is greater than x minus 1? Okay, so let's take 0 to be one end of the interval. So let's write it formally. F is continuous on, and I'm going to take the interval from 0 to, let's say, pi. On 0, pi. Why is f continuous on this interval? It's elementary. It's a difference of elementary functions, right? So that's one fact. F at 0, I know it's going to be negative because sine is bigger than x minus 1 at 0. Do you see that here? It's a bit small. Do you see that? So sine of 0 is 0, minus 0, 0, plus 1. So it's 1, which is greater than 0. I said negative, right? I meant positive. And f at pi, I can see that sine is smaller. Then subtracting something bigger is going to make it negative. What's f at pi? Sine of pi, 0. Minus pi plus 1. Minus pi plus 1. Okay, so I'm sorry that this is a bit small here. So it's minus pi plus 1, and pi is about 3.14, right? So minus pi plus 1 is less than 0. There we go again. So this is less than 0. Do you agree? Yes? So that's it. That's the conditions of the theorem. By the previous theorem, a function continuous on a closed interval, negative at one point, at one end point, positive on the other, has a root. So, therefore, let's see if I can wrap up this class without leaving the board. Therefore, I used to have a lecturer who would do his every lecture would start at that end and would end here, no matter how much he had to say. And it was really a convergence phenomenon. Because sometimes he would put like 3 theorems and 4 proofs in this little, but we're almost there, so that's not going to happen. It's bad. It's a bad habit, but we're really almost done. So therefore, by the previous theorem, there exists a C such that f of c equals 0. And saying that f of c equals 0 is saying that sine c minus 1 is 0, which is saying that sine c equals c minus 1. So we found a solution to this equation.
Say that since sin x is a bounded function and x minus 1, as the limit to minus infinity is minus infinity to plus infinity.
You're suggesting a different solution to this, to this problem. I would even, it's correct what you said, but so the statement was this is bounded, this is has a positive limit at infinity and a negative limit at minus infinity, therefore they must cross. I agree. Moreover, in this case, the picture is really convincing. There's nothing false about the picture. It's not that you're drawing some representatives. It's really 2 concrete functions, and there's the root. Okay? It's just an example. Okay, but it can be used even in situations where you don't know exactly how to draw the functions and things can be more challenging. Okay? Questions about these 2 examples? Everybody good? Okay, so let's take a 10-minute break now.